Hi everyone. Draw a chair conformation of cyclohexane has been a problem for lots of students, especially when they just started learning the stereochemistry. In this first example up here, we have a simple cyclohexane without any substituents on it. But we're going to put in all the hydrogen in order to get familiar with every axial and equatorial positions. So we can put in the axial first. So the axial bonds would be straight up or straight down. So here we have all the hydrogen for the axial, and then we're going to put in the equatorial hydrogen. Here we have the equatorial hydrogen parallel to this bond, and we have this equatorial hydrogen, it has to parallel to this bond, and then we have that one parallel to that bond, and this one parallel to this bond. So it always has to parallel to the bonds in the cyclohexane ring. And then we put in the hydrogen atoms. This is the simple cyclohexane ring with all the hydrogen bonds on it. And then we're going to now deal with the second example, the cyclohexane, which has two substituents on it. Down here, this molecule, we can ignore all the hydrogen atoms and we only put on the two substituents in its chair conformation. Now, first step is just randomly label all the carbons on the ring. We have one here, let's say this is 1, and carbon 2, carbon 3, 4, 5, 6. We can randomly label this chair form as well. Let's say that's 1, 2, 3, 4, 5, 6. And now we're going to put in our substituent. In this case, we can compare the example up here. We have two opportunities. One is up, one is down. So in this case, it's wedge up. Therefore, we're going to put on OH here. And there's a hydrogen axial, and we don't need to put it in. And then we have two hydrogen on the carbon 2. We just ignore the hydrogen. And then we're going to put on the T-butyl group on the carbon 3. And we can compare the first example here. We have two opportunities. One is up, one is down. The T-butyl group is pointing up wedge. So we have to put on up T-butyl group. And we actually have a hydrogen pointing down, the axial position, we can ignore it. Sometimes they're going to ask you in the questions how to flip the cyclohexane ring in chair form. In this case, the carbon used to pointing down, now it's pointing up. So we label it as 1, 2, 3, 4, 5, 6. So this carbon is actually this carbon 1 now, because we ring flip them. And then we're going to put on the substituents, the hydroxy group first. We have up and down opportunities, so we'll put it up here. It is axial. So when you ring flip, the substituent will change the original position. So if you have an equatorial OH group, now it will change to axial. And now we're going to deal with the T-butyl group. It used to be up, and now we need to put it up, because that's up, that's down. We have all the substituents on the cyclohexane ring, and the T-butyl group used to be equatorial, now it's axial. what is the most stable conformation. In this case, you can look at the structure. We have two big groups pointing axial, and it is 1,3 diaxial interaction. That means this conformation is less stable than the top one, because the equatorial of two substituents make the conformation more stable. Okay, I see you next time. Thanks for watching this video.